Hi everyone, today we are going to have a look at a vector equation of a line. So consider a straight line passing through 3D space. Defined by 2 points, P0, P. So as we have always done in this topic, we can define them with two vectors. Excuse me. So one here, let's call it R0, corresponds to P0, and a vector R here. Okay. As you can see here, it's quite straightforward. R. Okay, so let's call this vector the distance. The vector between these two, P0, P. Yeah. So it's quite obvious that R equals to the original plus the distance between the vector between the two. Yeah, so R here is the vector sum of this vector plus this vector here, plus this vector. So what can we do with that information? Well, let's consider another vector, say a random one. Like it doesn't even have to be fixed anywhere. So let's call it V. Imagine V, well, let's give the components A, B, and C. Imagine that only commonality between V and the straight line we're looking at is that they are parallel. Yeah, so these two are parallel. So in this instance, then we can represent this vector here, P0P, as a scalar multiple of what a V is. Yeah. So what we can do now is to write the vector representing this point, representing the second point here, in the form of R0 plus lambda V. Okay, what does this expression mean? Well, any point along this straight line is the initial point, your fixed point, plus a scalar multiple of some vector. So in essence, V here determines what direction you go from the first point, and lambda scales it, so it determines the distance. So together, what they're essentially doing is you starting with a fixed point, and then you go in a certain direction for a certain distance. And after that, you get the value of the second point. So in this case, for a specific value of R0 and V, then by varying the value of lambda, you can just get to any point. So for example, you're starting from here and you go in the direction of V. Yeah, so if lambda is large, the second point R is far away. If lambda is small, the second point. Yes, so this whole thing defines all the points on a straight line. Now, how does that help us? Well, okay, so this is where I have written earlier. Now, what this gives us is a set of parametric equations like what we did last time. So we have x equals to x0. Okay, so by the way, so this is our R, this is our R0 if it's obvious enough, and this is our V. Yeah, so x equals to x0 plus lambda a, y equals to y0 plus lambda b, and z equals to z0 plus lambda c. So once again, we have a set of parametric equations where the lambda value is the parameter. So by varying the lambda value, you change what x, z, y, and z are. And of course, the a, b, c here are called the direction numbers because the vector determines the actual direction you travel. Yeah. Alright, so how do we apply this? Now let's look at a simple example. Find the vector equation to the straight line joining points 5, 2, 6 and -3, 4, and 1, and then find the coordinates of the point on this line where lambda is 2. So how do we find it? Now suppose we have we represent these two coordinates a and b with two vectors. So let's call this one a. Yeah, let's start from origin and we get b. Of course, this is a and this is b, and of course we have a straight line passing through them. Well, straight-ish anyway. Okay, now equation to the straight line. So imagine if we have another point here, P. Yeah, and let's represent P with another vector R. Okay. You can see that the vector AB here defines the direction from A to B. And AP here, from A to P, this is a scalar multiple of AB. Because they are AP and AB are in the same direction. So AP is just AB multiplied by some real number. So we can write it as, and of course, P is defined by R. Yeah. So R, so for the arbitrary point P, the vector representing the arbitrary point P equals to your starting point. Yeah. So your starting point A plus, well, let's say AP. Yeah. Let's say it's this vector. So obviously, simple vector addition. And this one, R equals to A OA plus AP. Now, how do we define AP? Well, what we have is, we know it's a scalar multiple of AB. So we can say R equals to A plus a multiple of AB. And how do we find what AB is? Well, let's do it here. AB equals to, of course, it's B minus A. So -3, 4, 1, minus 5, 5, 2, 6. Yeah. So AB equals to -3 minus 5, -8, 2, -5. Yeah. Okay. So R equals to our initial point, 5, 2, 6. Yeah. So that's what A is. Plus lambda times -8 to -5. This part tells us that this is the direction. This is saying that it's the whole thing. You start off at A and you go in the direction of vector AB. So you go towards B. This is direction from A to B. Yeah, you go towards B. And then how far you go is determined by this lambda term. So in together, starting point, direction you go, and how far you go. And that would give us a point when we substitute a specific value for lambda. So specifically how far it is, yeah? So what we end up with is where lambda equals to 2, we end up with 5 to 6 plus 2 times -8 to -5. So we end up with -11. 2 plus 4 is 6. 6 plus -10 is -4. Yep. So this is the line that's value of lambda 2 in the direction of -8, 2, and -5. Okay, next one. Here is slightly different. So there is nothing to say that the line we are looking for will pass through either B or C. All this does is just providing us with a direction. So it's kind of similar to when you did Cartesian geometry and trying to find the equation of a line based on a single point and a value of m. Yeah, so the gradient. So the gradient tells you where to go. Yeah, you start from a point, you start it, and then the gradient tells you where to go, and you go a certain way. Well, this is identical. You're starting a point, and all these 2 points giving you is a direction to travel. Of course, this is different because the direction is actually a 3D vector, so it's a bit more complicated than a single gradient when you did Cartesian geometry. So let's look at this. Point A, that's pretty obvious. The direction, let's call this V equals to BC. Yep. So what we have here is it equals to obviously 3, 4, 1, minus 1, 2, and 3. So we get 2, 2, -2. Yeah. So this is the direction we have. Now, how we portray this? Well, imagine we have a point. Yeah. Let's say this is A, OA, and then a second arbitrary point. Let's call it R, goes to point P, just because we've been doing this way so far. Yeah, so we have a straight line here. Now, what's the condition imposed on straight line? Well, it has to be parallel to this line here, BC. That's the condition. So we can say that from A to P, the vector representing A to P is because they are parallel, so the distance from A to P is a scalar multiple of V. So we can just write it as this way. Okay, now this is pretty obvious what we are doing now. What R is original vector A plus this scalar multiple of BC. So it's A plus lambda V. So once again, starting point, direction, and scaling factor. So R equals to, obviously, we have 1, 3, and 2 plus lambda times 2, 2, -2. And if you want to write as parametric equations, it's x equals to 1 plus 2 lambda, y equals to 3 plus 2 lambda, and z equals to 2 plus, minus 2 lambda. So by varying the value of lambda, i.e. the position, the distance you travel in this direction, you can generate all the points. You can generate all the points along this line. So 1 lambda, you get 3, 5, and 0, and changing it just give you all coordinates of all the points along this line. Yep. Okay. Next one is kind of interesting one. So we are presented with two perspectives. Firstly, we look at these two. So these from P1 to P2 using or P1 as the fixing point. So we're looking at from the perspective of P1, and then we're going to use P2 as the fixed point and look at the line through the perspective of P2. All right, so how do we do that? Well, let's look at the first case. So from P1 to P2. Of course, let's do P1. Let's find the equals to, well, -1, 3, 3 minus 2, 1, 2. So equals to -3, 2, and 1. Yep. Okay, so in this case, how do we get the equation of the vector equation of the line? Well, this any point on the line has to be the same as your starting point plus a scalar multiple of the direction vector. Yeah. So this defines direction again, this defines distance, and this is this is the direction, this is the scaling factor, and this is your starting point. And of course, if we can write as the parametric equation of x equals to 2 minus 3 lambda, y equals to 1 plus 2 lambda, and z equals to 2 plus lambda. Yeah. And this is the perspective of the first line. Now let's look at from P2. So if we're using P2 as the fixed point, then let's look at P2 to P1. Okay, so it's just the reverse, the opposite of the last one. So it's 2, 1, 2 minus -1, 3, 3. So we end up with 3, -2, -1. Well, as expected, this vector is the opposite direction of this one. Okay, now we are going to construct a vector equation of a line from P2. So R here equals to, that's starting from P2, -1, 3, 3, plus lambda, -3, 2, 1. Yeah. Okay. And then to get our parametric equations, so here x equals to -1 minus 3 lambda oh wait, what I'm doing, sorry, apologies, plus 3 lambda y equals to 3 minus 2 lambda, and z equals to 3 minus lambda. Okay. What does this give us? So let's write the parametric equations down again. So P1, x equals to 2 minus 3 lambda, y equals to 1 plus 2 lambda, and z equals to 2 plus lambda. All right, from P2, x equals to -1 plus 3 lambda, y equals to 3 minus 2 lambda, and z equals to 3 minus lambda. Let's fix that. Okay. Now, the idea is if we substitute the value of point 2 here, so if we have x equals to -1, then correspondingly, we should get a y and z value of P2 as well. So let's try that. When x is -1, lambda equals to 1. So we substitute in. So x equals to -1, y equals to 1 plus 2 lambda, and z equals to 2 plus lambda, which equals to 3 equals to 3. Okay, so what do we have here? -1, 3, 3. All right, excellent. So if we find a parameter from P1 that generates the x value of P2, then we end up with the correct y and z value of P2. Apologies. Yep, and then if we do the same to P2, okay, let's say x equals to 2, then lambda equals to 5. Wait, sorry, lambda equals to 1. What I'm talking about. Okay, so here, when x equals to 2, y equals to 3 minus 2 times 1, which equals to 1, and z equals to 3 minus 1, which equals to 2. Yeah, 2, 1, 2. Excellent. So from the perspective of the second point, P2, if we find the parameter that would give you the x value of the first point, then the same parameter will also produce the correct y and z value for P1, which implies that these two sets of parametric equations actually describe the same line. Pretty cool, huh? So even though, well, actually, there's no even though. It's pretty intuitive. They're on the same line. Just because you're starting from one end rather than the other, it shouldn't make a difference to what the line actually is. Okay, for the last bit, something slightly amusing. Now let's go back to the 2 dimensions. Yeah, so we have a line. Yeah, so 2 component. Wait, sorry, this should be a B here. My bad. Yeah, so we have 2 vectors. Now we have a straight line defined by this. So we have x and y defined by x0, y0 plus lambda x1, y1. Okay. What does this give us? Well, it gives us 2 parametric equations, isn't it? So x equals to x0 plus lambda x1 and y equals to y0 plus lambda y1. So, well, what we can do is we can rearrange it. We can make lambda as the subject. So here, lambda equals to x minus x0 over x1. And here, lambda equals to y minus y0 over y1. We have now both the x terms and y terms expressed in terms of lambda, so we can just equate the 2. So x minus x0 over x1 equals to y minus y0 over y equals to 1. All right, how does this help us? Now we can rearrange this equation to have y as the subject. Then what we can end up with is a Cartesian expression of a straight line. So let's do it out. So multiply both sides by y1 and then plus y0. So y should equal to x minus x0 over x1. Everything is multiplied by y1 and then plus y0. Okay, so let's do some algebraic magic. y1x minus y1x. Actually, let's do it in alphabetical order. Minus x0 y1 over x1 plus y0. Let's give it a common denominator. So what we end up with is y1 over x1 x plus x1 y0 minus x0 y1 over x1. Yep. And what does this look like? Well, remember, x0 and y0 and x1, y1 are numbers. So this will give you a number, and this will give you a number. So it actually, you have the gradient intercept form. Yeah, so this is y1 over x1 gives you your gradient, while x1 times y0 minus x0 times y1 over x1, it gives you your constant term. And together they produces the equation in the gradient intercept form. Yeah, pretty cool, huh?